Alright, this is the last chapter that we have for grade 10, and it deals with energy. And what we're looking at, and if we can look even at this little diagram that I have here, is we're going to like tap into energy from grade 9. So there are different types of energy that we have. Let's say, for example, I'm looking at this Ferris wheel. Now, how does the Ferris wheel work? The first thing I need is a power source. And that power source is usually chemical energy. And that chemical energy goes from chemical energy, because inside your power source you have chemicals, because like batteries and so on, or fossil fuels. And then it becomes electrical energy. Oops. And then from there, how do we get the Ferris wheel around? It gets converted into kinetic energy. Right. So each time you can see that I'm using this word energy. So what does energy mean? So when we talk about energy, we say energy in physics is the capacity for doing some sort of work. That's important, because when you get to grade 12, this becomes a very important concept that we have to deal with. So it's the capacity for doing work. So if I'm doing work, I am using up energy. And if I possess energy, I can do work. So that's what we deal with when we talk about energy. We also know about energy that we know that with energy, so I'll put this in here. Oops. We know how much, it's a quantity that describes how much work an object or system can do. Alright, I'll just color this up. Oops. So when we're talking about energy, we also need to understand that energy is just like when we look at matter, right? And what we know about energy is that, oops, so undo that. Right, we know about energy is that just like matter, it cannot be created nor destroyed, and we're going to get to that in a little bit. All right, so we've got chemical, electrical, kinetic. In this section, we're going to be dealing with quite a bit of energy principles or ideas about energy and the different types of energy that we can get. For example, so when we talk about energy, we know that energy is present everywhere. Every subdivision of an atom in a molecule of any matter or object possesses energy. There's different types of energies, and we look at things like, oops, there are two types of energy that we're going to look at in quite a bit of detail, and that's kinetic energy, which is the energy of movement, and potential energy, which is stored energy. So when we look at it, they belong to two very specific categories. If I'm looking at kinetic energy, I've got thermal, mechanical, electrical, and magnetic. If I look at potential energy, I've got chemical, elastic, nuclear, and gravitational energy. Right? Ways in which we deal or experience energy, we can also have sound energy and light energy. And we worked on sound and light when we did transverse waves, longitudinal waves, and electromagnetic spectrum. So these are the different types of energy that we will come across and that we will work with. Alright, so the next thing I want to look at is, please make sure you get this diagram into your book, or you get these notes into your books. Very important, because they'll ask you, name the types of kinetic energies, name the types of potential energy. You need to be able to answer those types of questions. Alright, so let's have a look at our key concepts. Alright, the first thing we're going to be looking at is, we're going to look at potential energy. And when we look at potential energy, we're going to be looking at potential energy at a height. And when we look at it at a height, it's actually called gravitational potential energy, right? Not just potential energy, but we'll get into that in a little bit. The next thing we're looking at is kinetic energy. And we've looked at kinetic energy this year in chemistry, and we related kinetic energy to temperature. All right, and we said that if we increase the kinetic energy, it's like increasing the temperature of something. But here we're going to look at it in a more physical way, or in physics rather. And then we're going to look at what do we mean by kinetic energy. The next one is mechanical energy. Mechanical energy talks about combining these two. So if I had to combine potential energy and kinetic energy, I'm going to get mechanical energy. And if I have if I have mechanical energy, I want you to think of energy in the same way as we spoke about mass. That mass and matter and so on, when we deal with chemistry, we know that charge is conserved, matter is conserved, cannot be created nor destroyed. So when we deal with energy, we know that with energy I can only transfer energy. So we're going to look at the conservation of mechanical energy. And there is a reason for conservation, because I want you to think about it like this, that energy can be stored or transferred. But that's about it. Alright, so these are your key concepts. We're going to look at formulas, we're going to look at calculations, we're going to get into the nitty-gritty of this topic. Right, so the first key concept that we're having a look at here is gravitational potential energy. So when we talk about potential energy, we're talking about stored energy. All right, we have all this energy that's stored and built up. And what we mean by potential, it means the ability to do something. All right. And this something is important because that means you have the ability to do anything. So when we talk about gravitational potential energy, we are talking about energy an object has due to its position. All right, so that's what we mean by a potential energy. The fact that we're using the word has means that it is stored. So what you have inside of you. Now, in this section specifically, we're not just looking at your position, right? We're looking at your position relative to a field. So what's actually happening is, if I had the planet Earth here, around this planet Earth, there's a field being generated. And if I'm in this field, I'm just going to show you now. If I'm in this field, let's say, for example, I'm at point X there, or I'm over there at point Y, or I'm over here at point Z. No matter where I am, as long as I'm in this field, I'm going to experience attraction. Where am I experiencing attraction? To the center of the earth. So the attraction to the center of the earth, that is called gravity. I'm attracted to it. So if I'm within, so if you see this dotted area, that is what we call the gravitational field. And if I am within this field, if I'm in the zone here, right? If I'm in the zone here, that means I'm going to experience an attraction towards the center of the earth. So what that means is, what does that attraction mean? So what I mean by attraction, it means that you're going to be pulled towards. Now, that doesn't just happen at a random sort of thing. So what's happening at all times, right? At all times, we are falling towards. We are falling towards. I'm just moving this up. Let's move this out of the way. Right. We are falling towards the center of the earth. Now, when I say falling, remember we spoke about in motion, we spoke about free falling. Right. And if I'm falling towards the center of the earth, right, because that's where the gravitational pull is happening, from the center. If I'm free falling, it's happening at the symbol we're going to use is G, which stands for gravitational acceleration. Right? It's the acceleration at which you are falling. So G, which is a vector, is equal to 9.8 meters per second. And remember, we're always going to take downwards as positive, because you are falling, and like I said, if that's the planet, you are falling towards the center. No matter where you are, you're going there. Can you see where the trajectory is? You're falling downwards. And when you fall downwards, it's a constant. You'll find it on your formula sheet. That means that when you see G, or the symbol G, we're talking about gravitational acceleration. So when we talk about gravitational acceleration, right, we're dealing with situations, and I'm bringing this definition up here. We're saying that an object will have potential energy if it is kept at a height, and that's called gravitational potential energy. All right, so if something is at a height, let's say for example, I'm in my classroom. So let's just imagine that. So here we are. Let's do this a little bit differently. That's the corridor. That's that pillar over there. And let's say I'm standing outside my classroom. Right? And in my hand, let's say I have a ball. Right? So let's just talk about the height here a little bit. What we mean by that. The first height that I have is that from where I'm standing, there's a height. Let's say that's height 1. If I look at another kind of height, don't forget, I'm on the first story. So I've got a height from there to there. That's the height of the ground. Right. But also there's another height. From this area here, I can go all the way down to the center of the earth. So that's another height. So what's important to understand about that height number 3? What's important to understand about this height here is that the height is not always to the center of the earth. Right? We can say the height is relative to the frame of reference. Right? The frame of reference, we've discussed this before. What we would consider a start point. So let's say I wanted to know the gravitational potential energy of the ball from the floor. Then if I'm looking here, it's going to be this blue one over here. It will be height 1. Does that make sense? You should be drawing all of this in your books. If I wanted the gravitational potential energy, right, from the ground floor, then I would be looking at height 2. So can you see here, that's from the floor, this one's from the ground floor. Those are two different values. So that is what we mean by the frame of reference. It is relevant to that sort of situation. Right, so when we talk about gravitational potential energy and we're talking about the fact that it's kept at a height, also, let's get into this now. What you need to understand is that if I'm close to the center, right, of the earth, that means I have less potential. Think about it like this. Like with the ball that I was going to hold here and I was going to drop this ball to the ground floor. It has further to go if I was going to say center of the earth. But if I was going to say the floor, it doesn't have that far to go. So the closer you are to the center of the earth, or even I can say, sometimes we're going to use the frame of reference. Then you have less potential. If I am far from the, I'm going to say center of earth, but also the frame of reference, then I'm going to have more potential. And remember, we spoke about potential. When we talk about potential, it's the ability for something to happen. That something could be anything. If I'm holding that ball, it has, if I think of this ball, it's got quite a bit of potential because I can either drop it, I can throw it up, I can throw it across. All of these things mean it has the potential, or it has the potential, right? Another thing that we can't keep doing is writing that. Gravitational potential energy, gravitational potential energy. So what we're going to do is, in this section, right, or in this section in grade 10, and it becomes very important when you get to grade 12, is that we're going to be looking at gravitational potential energy, right? So I can't keep saying gravitational potential energy over and over again, so I'm going to say, when we do calculations, we have formulas. So I can say that the gravitational potential energy is equal to the mass of the object multiplied by gravitational acceleration multiplied by your height. So that's what our formula looks like. So if I think of gravitational potential energy, the symbol we use is capital letter E, subscript P. And if you look at older textbook, you might see them use the letter U, capital letter U. Is equal to mass. The symbol for mass is M. The symbol for gravitational acceleration is G. Oops. And for height, it's H. Energy, right? Any type of energy that we're looking at. Please make sure you're writing these things down and you're highlighting it and so on. Any type of energy is measured in something we call joules. And we're going to use a capital letter J as the SI unit. So the symbol is EP, the SI unit is J, and the measurement is joules. Joules is a scalar quantity. And what that means, it means it only has magnitude. There must be no direction. So when you're doing these calculations, you must have no negative values. So make sure you check that out. M over here is mass of the object, and in physics, mass is always in kilograms. Don't forget, this is important because like I just said now, in physics, mass will always be in kilograms. In chemistry, mass is always in grams. Very, very, very important. If you make a mistake, you're in trouble. Which means you need to know how to go from kilograms to grams. So if I have 1 kilogram, you have 1,000 grams. So times 1,000. Please remember that. That's important. G over here is gravitational acceleration, and we know that that's always going to be at 9.8 meters per second squared. And H over here is your height, which is always going to be in meters, and your SI unit is going to be little m. This one should be kilograms. And that is your formula for potential energy. So another thing that you also need to understand about this gravitational acceleration is that the first thing is you can only experience it if you are within the field. That's the first thing. And the second thing is it changes for every planetary body. That means the gravitational acceleration on Mars, on Jupiter, on Earth, on the Moon, every single planetary body has their own G value, which you could be asked to work out or whatever the case is. So this is all about gravitational potential energy, and all it looks at when we talk about gravitational potential energy, I'm looking at the ability for something to happen. And let's say for example, I had a pen. Right, let's say I had this pen, and there we go. Right, I have this pen over here, and I have my work desk here, right, and I have the ground here, and don't forget there's a classroom that's directly underneath me, so that's over here, and then I've got all the way to the center of the earth, and that's the earth's core. So when I'm talking about the potential for something to happen, is I could take this pin here and I could throw it this way and I could throw it upwards, right? And if it gets thrown upwards, let's say the frame of reference is this desk here. If it gets thrown upwards, it will gain potential energy. If I throw it down, it's going to lose potential energy. Now that's a bit weird. Gain and lose, right? We just said that you can't destroy or create energy because it's just like matter. So what we mean is between this situation and that situation, like there must be some sort of conversion happening. Right, so that's the first thing that can happen. Like I said, I could use my classroom floor as a frame of reference. And can you see there? If I'm dropping it, it's going to lose potential energy. And what we've got to do is understand, like let's say for example, this is at a height of 1 meter. And when it falls, it's falling with a gravitational acceleration of 9.8 meters per second. So, what you need to understand about this is that where you drop it from, and I'm reiterating this because you're going to get confused, all depends on the frame of reference, right? Each time the frame of reference can change. So if you have a look at all my different heights here, and I've said this before, it could be in any one of these zones. So when we talk about potential, I can drop it, I can throw it, I can let go, it will fall. It's all dependent on the height of whatever I'm dealing with at that sort of situation. Does it make sense? Right, let's have a look at example 1 for gravitational potential energy. Now let's have a look here. We're starting with example 1. Right. Just have a look at this question. Oops. Move that here. Right. A boy of mass 30 kilograms climbed onto a roof of a garage. The roof is 2.5 meters from the ground. Right. So let's just sketch that quickly. I've got this sort of setup here. Got a boy over here standing on the roof. Yay. The height here, and guys, have a look how I do this. I draw myself a picture so that I have a good idea of what I'm actually dealing with. So here I've got a height. The roof is over here. It's 2.5 meters from the floor to the ground over there. Right. The boy himself, let's draw that properly. The boy is 30 kilograms. So I've got a mass here of 30 kilograms. So I'm writing all of my information down before I even begin. So I've got that, I've got that. Let's look at A. A says, how much potential energy did the boy gain by climbing onto the roof? Right, so I know that my formula is EP is equal to M, G, and H. I've got the mass, I've got the height, because they want at the top here. So for question A, they want the gravitational potential energy at the top here. I also know that G, no matter which calculation I'm doing for G is equal to 9.8 meters per second squared. Alright, so I'm just going to put my information in. The mass is 30. Please make sure you write down the question and you write down the solutions. I would suggest writing down the question first and then continuing from there. So 30 times 9.8 times 2.5. Pop that into your calculator and you're going to get 735 joules. Right, so what I'm looking at now is they're telling me that when I'm here at the top, I've got 735 joules. Just want to move this little bit of information here. Right, so that's the one thing. Look at the next question. The next question says to you, now the boy jumps down. Right. So this is important. What we need to understand that here on the ground, that is our reference point. Everything is with reference to that ground point. Right? So the ground. He jumps down. What is the potential energy of the boy when he is 1 meter from the ground? So if this distance here is 2.5 meters that I'm looking here, then I need 1 meter off the ground. So let's say I say, for example, 1 meter is there. So that's 1 meter. So if I'm looking at B, my information is a little bit different. I've got mass here still at 30. I've got G, which is still 9.8. But I've now got a height, which is equal to 1 meter, not 2.5 meters. So now they want to know the calculation for what's his potential energy. So EP is equal to mgh, right? The mass value we know is 30, the G is 9.8, and the height is 1. And you pop all of that into your calculator, and you're going to get 294 joules. Right, so at this point now, for question B, you are sitting at 294 94 joules. Now, if I'm looking at those two situations from here to here, how could I start with that and end up with that? Where did all the energy go? So we remember I spoke about how we have energy that is lost. Now, when I mean lost, it doesn't mean it's gone, because remember I can't destroy it. It means there was a transfer. And we're going to get to that in a little bit when we discuss the next question. All right, let's have a look at the next one. C, for example. Let's go C. What is the potential energy of the boy when he lands on the ground? So now the height is now equal to 0 meters. Now, if I just say EP is equal to mgh, it's going to be 30 times 9.8 times 0. And anything times 0 is 0 joules, right? Now, why is it that when he's on the ground, there is no potential energy? Because you need to understand this. There is no distance, and what we're talking about is height, eh? There's no distance between the object and the frame of reference. So they're going to ask you, why would the potential difference be 0 when the boy lands on the ground? Is you must recognize, if there's no height, there can be no potential energy. That is very, very important to understand of this topic, right? So once we've done that, we need to go and look at this situation. What do we mean by the energy was transferred? So what happened from point A to point B there? That we went from 735 to 294. If we cannot create nor destroy energy, right? So let's go and have a look at the next one, which is called kinetic energy. All right, when we talk about kinetic energy, we must understand that kinetic energy is energy an object has due to its motion. So if I have any moving object, it will have kinetic energy, right? I want you to understand the same situation. Let's say I had that ball, holding that ball. And if I'm holding the ball, right, so let's say I'm holding the ball. Let's say I am holding the ball, right? Then I can say that the ball is either stationary, I can say the ball is at rest, and if that happens, then the velocity of the ball is 0 meters per second. That is if I'm holding it. Makes sense? Now, if I'm holding it, it has potential. So I can either drop it and it falls down, or I can throw it up. Now, if I do either one of these, whether I throw or I let go, the ball will move. And when the ball is in movement or in motion, when the ball is in motion, it means that the value for the velocity cannot be 0. So the velocity must be greater than 0 meters per second. And when the ball has a velocity greater than 0 meters per second, right, then I can say also at the same time, I can say that it has or possesses kinetic energy, right? So kinetic energy in essence is also a scalar, But inside this formula, in this formula for kinetic energy, which we're going to look at now, it has a vector quantity, which is velocity. So let's have a look. Please make sure you're getting these notes down. Let's have a look at the formula for kinetic energy. So the formula for kinetic energy is kinetic energy is equal to half multiplied by mass of the object times velocity squared. So when I'm writing it down, the formula is capital letter E, subscript K, or if you check all textbooks, you might have the value K is equal to half times mass multiplied by, let's write that a bit better, V squared. Over here, we know that kinetic energy is measured in joules with a capital letter J, and it is a scalar quantity. So no direction. The next thing is the half. That's fine. You can also, when you put in your calculator, you can use 0.5 if that makes you feel comfortable. M over here, mass of the object in kilograms. And the SI unit is a little k with a little g. Alright, don't forget, you cannot work with grams. The last thing here is the velocity. The velocity here is measured in meters per second. So m dot s to the power of -1. Makes sense. And it must be squared. So please make sure that when you're putting your information in, you use brackets. Right, now this velocity. Velocity is a vector quantity, which means it can have positive values and negative values. But in this situation, what you need to understand is that even if it is negative, you can never have a negative answer because it's going to be squared. And if it's squared, it's going to be a negative times a negative, which is going to give you a positive value. So with your velocity, you might have to put a negative value into the formula, right? You can have a negative value or positive value, but in the end of the day, your answer will have to be positive because that value has to be squared. So here's your formula. You find it on your formula sheet under the mechanics section. This is your formula for kinetic energy. Right. In the instance that, let's say the velocity is 0. Right, let's say the velocity is equal to 0 meters per second. Right. When that happens, that creates a situation where you cannot have EK, or rather kinetic energy. And let's see how that works. Because let's say, for example, I had an object that had a mass that is equal to 1 kilogram. And I said that EP is equal to half mv squared. Half times the mass, which is 1, times the velocity, which is 0. And all of that is squared. So can you see how I put the brackets in? So when I put it in my calculator, I better put it in like this because the calculator is not as smart as you are. And then notice that I've got half times 1, right, times 0 is going to give me 0 joules. Alright, so in this situation, if the velocity is equal to 0, oh, that's an EK, sorry. If the velocity is equal to 0, there can be no kinetic energy. So let's look at it in a little, let's look at a little example. Let's look at example 2. Alright, please get this example into your books. All right, we're looking at example 2 here. It says a car with a mass of 700 kilograms, right, is traveling at a constant velocity of 100 kilometers per hour. Oops. All right, so I've got a mass here. Oops. Mass of 700 kilograms, velocity of 100 kilometers per hour. So let's just have a look at the information that I have here. I've got my vehicle, right? My vehicle's driving, and the vehicle has a mass of 700 kilograms. Great. And it has a velocity of 100 kilometers per hour, which can also be written as 100 kilometers per hour, which you're used to. However, velocity is always in meters per second. So when we did motion, I gave you that conversion. So you need to make sure you go and check the conversion. So if I want to go from kilometers per hour to meters per second, if I'm going from here to here, I must divide by 3.6. So I can't use this value at all. I need to convert it. So I'm going to say 100 divided by 3.6, and I'm going to get 27.777778 meters per second. So the value that I'm going to use for velocity is that value. Velocity is equal to that. So you're not allowed to use kilometers per hour. You must do a conversion. Now they want us to calculate the kinetic energy. So EK is equal to half mv squared. So half times 700, right, times 27.77778 is going to give me 270,104.94 joules. If you want to, you can put it into scientific notation. You're more than welcome to do that. But that's how you would do something like this. And I'm going to do another example with you for potential energy and kinetic energy and a little exercise. And then you're going to watch a second video that's going to do mechanical energy and the conservation of mechanical energy. That's your last two key concepts. So let's just have a look at this next thing. All right, let's have a look at this question. It says a bird flying over the sea has a weight, undo that, has a weight of 15 newtons and has a constant 765 joules of gravitational potential energy. How far above the sea does the bird fly? Right, so if I'm looking at this sort of situation, I've got the ocean here, or the sea rather. So now my sea is now my frame of reference. All right. Above here, I've got a bird. So I'm just going to draw my little bird. All right, I've got my bird flying. And I know that the weight of the bird, weight is a vector quantity, is 15 newtons. And I also know that the EP value, the gravitational potential energy value, that's constant, is 765 joules. All right, so that's my setup right now. They want to know what is this value here. So they want height. So in terms of height, I don't know. So what information do I have? Or what do I need? I know that EP is equal to mgh. I know the g value is 9.8 meters per second. Right. I don't know the height. I don't know the mass. Right. But in terms of mass, what I do know is I know the weight. Now weight is a force. But the formula for weight is W is equal to mg. Right? And I know this value W. And this g value, remember what I said, is the same value. It's a constant. So I can use this formula, which can look something like this, which is W is equal to mg. And I can say that I want mass. So mass is equal to the weight divided by the gravitational acceleration. So mass is equal to the weight, which is 15, divided by 9.8. And I'm going to get a mass of, let's just move this, I just want to reduce this, 1.53061224 kilograms. Right. So I've got my mass now. So do I have mass? Let's have a look at what information I've got. Do I have mass? Yes. Do I have G? Yes. Do I have EP? Yes. So all I'm going to do is I'm going to take that and put it into my formula. Let's go here. And I'm going to say EP is equal to mgh. And I'm looking for the height. So my EP is 765, which is equal to 1.5306122. Remember, when you have got to write all of these decimals out, because that's just how life is for you guys. 9.8 times height. So now what I'm left with is 765 is equal to 15h. Right, so what you should notice now, here's the cool bit. Have a look here. In my formula, I've got mg, which is also the weight. So what I'm trying to show you is that when you're in this sort of situation, there is a way of getting the mass. There is a way. But also you need to realize that EP is also equal to the weight times the height. So it's a sideline formula we don't give you. But you need to actually know that mg stands for the weight. So 15h. So all we're going to do now is we're going to take the 765 on both sides and divide both sides by 15. And the 15s are going to cancel each other out. And I'm going to get a height is equal to 51 meters. And height is a scalar quantity. Make a note. So therefore, it means I don't need any sort of direction. So how far above the sea does the bird fly? The bird is flying. The bird is flying 51 meters above the sea. Does that make sense? So you need to start seeing beyond these types of questions. So this was example, should have written that down first. Example 3. All right, let's have a look at example 4. Ooh, let's do this here. And let's say example 4. All right, if we have a look at example 4, it says, what is the mass of an object that creates 33,750 joules of energy? It's traveling at 30 meters per second. So in terms of mass, I've got nothing. In terms of energy, I've got, now remember, it is traveling. So I have to have EK. My EK value is 33,750 joules. And my velocity is 30 meters per second. Right? So all I'm going to do is write down my formula. EK is equal to half mv squared. You get a mark for that. Then I've got half times the mass, which I don't know, times the velocity, which is 30 squared. Right, let's have a look at that. So now what's a half? So I've got a half times 30 squared. So 30 squared is 900. Half times 900 m, right, which is the mass. And don't forget this is 33,750. Keep bringing this down, sorry. All right, so I've got 33,750 is equal to half of 900. So 900 times 0.5 is 450 mass. Now I want this mass by itself. So I'm going to divide both sides by 450. 450. That will cancel out. And I've got a mass now of 75 kilograms. So that is your mass of your object. So when you're working with this, you need to make sure that you using mathematical skills, and the mathematical skills that you're working with is equations. So this is why we do maths and science at the same time. You need a knowledge of equations in order to do these types of calculations. Now, let's say you're doing maths literacy, for example, they don't do equations. So how would you be able to do equations, complicated equations, if you weren't doing math? So there's a reason why we do mathematics and physical science at the same time. Let's have a look at example 5. I want to look at another velocity one before I give you an exercise to do. All right, I've got here Missy D. Water, a former platform diver for the Ringley's Brothers Circus, had a kinetic energy of 15,000 joules. Just prior means before, to hitting the bucket of water. If Missy's mass is 50 kilograms, what was her velocity? Right, so they're telling you we have kinetic energy. So I'm going to write EK here is equal to 15,000 joules. And they're telling us her mass was 50 kilograms. What we don't know is her velocity. So that's what we're looking for. So when we put it into our equation, we're going to go EK is equal to half mv squared. All right, this squared here, this is a different kind of example, so please make note of this. I don't want velocity squared, I want velocity by itself. So the EK is 15,000 is equal to half times the mass, which is 50, multiplied by v squared. So now I've got 15,000 is equal to half of 50, which is 25 v squared. Now I need velocity. So the first thing that I need to do is I need to isolate the v squared. So I'm going to say 15,000 divided by 25 on both sides. Right? So we're going to divide by 25. That's going to cancel. Divide by 25. And I'm going to get v squared is now equal to 600. Right. Now here's the thing. They don't want the velocity squared. They just want her velocity. So I need to get rid of that square. So the best way to get rid of a square is to square root. But remember, whatever I do to the left-hand side, I must do to the right-hand side. So I'm going to put a square root over here. And I'm going to put a square root over here. So this is why this is important, because I want velocity, not velocity squared. So if I put a square root over this left-hand side, then the square root and the square will cancel each other, and I've got velocity. The square root of 600, all right, I'm going to get 24.4949489 and so on. I must make sure I must round off to 2 decimal places always. So I'm looking here at this number, which is 4. So I'm left with v is equal to 24.49 meters per second. And because it's a vector quantity and it was positive, then I can say in the direction of motion. So can you see that when I have a vector quantity, I have to make sure, I can just put that over there, I have to make sure that I put a direction with my answer because it is a vector. All right, I'm just going to put up some questions that I want you to do. You need to do those questions before you watch the next video. All right, if you have a look at this activity, please make sure it's a worked activity. So it's an activity on the 2 types. All right, please make sure you get down the questions and the answers into your books. Once you're done with these types of questions, you're done with all of this, you should send me your work, and then from there I will give you solutions and so on and so on. All right, the first thing they want you to do is they want you to, I'm just going to highlight the main thing. They want you to classify, oops, they want you to classify the following, where am I going? Whether it's potential or kinetic energy. Right. The second question, they want you to find examples in your home that are examples of kinetic and potential energy. Then if I look here, question 15, they from question 15 to question 25, they're giving you calculations. They all simple calculations. Please make sure that when you do these calculations, you have the right conversions. They're quick calculations, they're small calculations. The maximum amount of marks you can get is 3 or 4. But remember, it's part of the bulkier side of your examination because it's a new topic and you haven't been tested on it before. So please make sure that you do this work. So you've got questions 15, 16, and 17. Then you've got 18, 19, 20, and 21. Please make sure these questions appear in your books. You can either write all the questions on and do the calculations, or question, calculation, just so you can get a little bit of practice. And then you've got questions 22 to 25. So you can pause the video and you can see I've been talking in between each section. You can pause the video, take down the questions, do the calculations, and then keep going for the rest of these. These are the main questions that you need to make sure that you answer. Once you're done, like I said, send me your work. I will send you some solutions, and then you can watch Mechanical Energy 2, the second video of this chapter. Alright, I'll see you guys in the next video. And before I say goodbye for this video, make sure you send me everything on WhatsApp so that we can keep track of if you're doing your work or you're not doing your work. Please make sure it's done. I cannot stress enough how important this section is.